So we talked about sets, and then we moved towards functions, and then we saw how could we have some sort of functions, some sort of relations as well, and some sort of predicates as well. And then we moved towards graph, which is again important thing that you need to mathematically model any sort of problem. And then we switched towards languages. We talked about language, what it is, and then we saw it is somehow based on the strings that you can have. So it is a set of strings you can have. And then we moved towards definitions and theorems, and then we talked about that as well. So what do you mean by theorem, and then how could you somehow prove that theorem, okay? And I would be somehow continuing the same mathematical foundations that we learned in the last class, and then I'll show you how could you prove those theorems. Before I move towards different types of proof, guys, I would be telling you about conjectures. So precisely if you talk about conjecture, guys, so this is somehow, possibly true, but no proof has been constructed for that case. And if you have proof for that theorem, guys, that would not be conjecture, because that would become a theorem, because you have a proof for that. So if you talk about proofs, so we talked about theorems, and then, you would be eager about listening about proofs. How could you prove that theorem, And there are three ways you can prove a theorem. And one is proof by construction, the other one is proof by contradiction, and the third one is proof by induction. First you have to identify what kind of theorem you can have. So we can have a theorem of form some object A exists. We can have some sort of theorem. So I'll give you example later on, and then things will be more clear. Now you have to show in the proof how to construct A. Now I'll give you example, and I think things will be more clarified when I would be explaining you about example. So if A and B are real, and these can be real numbers. This can be 1, 1.5, 2, 3, 4, 5, 6, any number can be there. And A is not equal to 0. This is quite important over here, okay? Then there exists a R such that AR plus B is equal to 0. Now, we are claiming there exists a R. That is making this equation as AR plus B is equal to 0. Now, what do we need to prove here? We have to prove that this R exists actually. We are saying this R exists, so we have to construct this R. How would you construct that? Let's look at that proof as well. So you can have an equation AR plus B is equal to 0. And you can just simplify this equation. You can take this B on the right-hand side of equation, and then you can find a value of R, which is minus B or A. This means that you are constructing R from the given equation that you have in the theorem. Okay? Now you have somehow constructed R from the given sort of evidence that you can have in the theorem. Now how could you somehow imagine that this is the true value of R? You can do the verification as well. So how would you do verification? Yes. You just take that initial equation, and then you place the value of R in that equation. And then you keep on simplifying that equation until you get some sort of simplified expression. And that could tell you that this is somehow the true value of R that you have come up with. Okay? So if I summarize this whole story of proof by construction, so I can say that you somehow claimed something, that this exists, and then you came up with construction of that thing. So let's move towards proof by contradiction, guys. So what kind of theorem you can have? P is true. For example, I can have, okay, AR plus B is equal to 0. So this is something true. And what exactly you have to do? You have to assume that P is false. And you have to do some hypothesis over here. You have to do some sort of mathematical reasonings. And you ended up with what? That the thing that you have taken as false at start, that is not indeed true. So what exactly that is? That is true. You took something false, and then you are trying to prove that thing false. But you end up with the thing that this false is not true. So what exactly that is? That is something true. You got this point? So you are somehow taking some wrong assumption, and then at the end of the day, you are contradicting that assumption. So this means that contradicting that assumption means that this was not indeed false. That was indeed true. And this is what you want to prove. The claim that I did that P is false, that is indeed false. So this means that that was not false. It was true indeed. And this is what you want to prove. So I could modify my last theorem that I gave you in the last slide. So I have if A and B are real and A is not equal to 0, then there exists a unique R. So this is quite important point I added into this theorem. So I added a word unique over here. Unique R such that AR plus B is equal to 0. We have to prove that R exists. Now, this theorem somehow looks very similar to the theorem that I have taken in the case of proof by construction. So how would you judge in your mind? You have to use proof by contradiction, not proof by construction. This unique word would be compelling you that, it's saying there is a unique R, but what you claim in your proof that this is not unique. There can be some S as well. And then you prove that as false. That would tell you that this is something true. That was not false. Okay, so let's start with a proof by contradiction. So I have AR plus B is equal to 0. Okay. Yes, AR plus B is equal to 0. Now what I have to do over here is that I have to suppose that we have two R. One is R, the other one is S. So we don't have a unique R over here. Unique means there is only one R. But I'm taking something opposite of that. I'm saying there is another instance of R which is S. And that would also be equal to 0. When I say AR plus B is equal to 0 theorem, so if I say there is some other instance of R which is S, so I can say S plus B is equal to 0 as well. Since both of these equations are equal to 0, I can say both equations are equal to each other as well. I keep on simplifying these, values, these equations. I end up with R is equal to S. So S. Yes. So what was my claim at the start?
There exists more than one.
There is one other instance of R, but here you can say it's saying R and S are both same. So this means that you can't prove that R and S are different. So what exactly you can say? That R is unique. So this is how you can use proof by contradiction. And this is some sort of method that is quite vital. Sometimes you can't come up with proof by construction, and then you guys would be saying, okay, I can't come up with the proof of this theorem. But when you go with proof by contradiction, and then you would see things would be easier a lot, as you can see over here. Got this point? So this is how you can say that by proof by contradiction that your R is unique. The third proof is proof by induction. So you can have a theorem like this: P is true for all I greater than equal to 0. I is somehow the domain of the function. Okay, so if I say P of I is true, P of I is true for all I greater than equal to 0. This means that I can place a value of I as 0, 1, 2, 3, 4, 5, up to so on and so forth. Whatever value I can have. And then that P should be true. So how would you do this? So you have two cases for the proof of this kind of theorem. You have a base case and then you have an induction case. So base case is, quite evident, like you have to take a value of I is equal to 0 for this case. And what is induction case? That is what exactly you told us, like we have to assume P of I is true. And by using that, we have to prove P of I plus 1 is equal to, is also true. And I can be any value. If I place I is equal to 0 and then Pi plus 1 would become 1. And if I take I is equal to 100 maybe, and then Pi plus 1 would become P of 101. So in this way, if you go with induction case, this would authenticate like it is true for every value of I greater than equal to 0. And if you can prove both of these base induction cases, you can say this P is true for every I greater than equal to 0. Let's go with a proof of, a theorem, and then that could make more sense about proof by induction. So for example, I have to prove that 2 raised to power n is greater than 2n for every positive integer n greater than 2. And now I have taken n greater than 2. This means that n starts from 3, not from 0. Now what would be the base case for this problem?
N is equal to 3.
N is equal to 3 would be base case for this problem. Base case is the very first value of that argument. So if you put 3 over here in the equation, that is 2 raised to power 3 greater than 2 into 3, and you can see 8 would be greater than 6. And that this base case can be easily proved. And if you talk about induction case, guys, so you have to assume P of k is true, and then you have to prove that P of k plus 1 is also true. Okay? Now how could you do this? What is P of k in our case? That is 2k greater than 2k. 2 raised to power k greater than 2k. Now what would be pk plus 1? That would be 2 raised to power k plus 1 greater than 2 into k plus 1. So I'll start with the left side of the equation, left side of the inequality, which is 2k plus 1, and then I would prove it is greater than 2k plus 1. And I can use this as assumption, because this is P of k for my case. Okay? So what exactly I can do over here? So I can start with 2k plus 1, and I can write it as 2 multiplied by 2 raised to power k. And I know that 2 raised to power k is greater than 2k, and I can say 2 multiplied by 2 raised to power k would be greater than 2 into 2k. So this is quite simple. Like, you know, this can be concluded from this assumption. And then this would be true. Okay? And what I can say about this 2 into 2k, I can take 2 as common, and it would become 2 into k plus 1. And I can say that 2 raised to power k plus 1 is greater than 2 into k plus 1. So this was what I want to prove at the end of the day. I can see over here. Okay, so this means that I have 2 raised to power k plus 1 is greater than 2 into k plus 1. Now, you know, you can somehow go with base case and then induction case, and you can prove any of the proof that you want to prove. And then we have finally structural induction. So structural induction is more towards, you know, graphs, guys. So you could see over here, so we can say P is true for all nodes of tree. We have a tree, something like this, and then you can say some property P is true for every node of the tree. This would be some sort of question for you guys. So how could you prove this using structural induction? You again have two cases, base case and you know, induction case. Base case is that you have to prove this for the case of root, which is the top node in the tree. You know, and then the case is that you have to assume maybe I have to prove P for this case, and I have to assume P is true for this as well this. So P is true for every ancestors of X. Now if my current node is this one, I have to prove a property P over here in this node, so I have to make an assumption that it is true for this one, and this one until I reach the root of the node. So I'm taking all those ancestors.